Steinhauer here, welcome back. Continuing our discussion of evolution of stars. We've seen how in the past class stars can be formed, and we've even seen how they can evolve from protostars onto the main sequence where they become stable hydrogen burning stars. In this chapter, in this class, we're going to see what happens to stars after they run out of hydrogen in their cores, where they move on the HR diagram, how they change in luminosity and temperature, and what will eventually happen to them when they die. So here we go. Stars from adolescence to old age, chapter 22. We need to break this discussion up actually into two parts because very different things happen for low mass stars and high mass stars. And here's a quick graphic to show you sort of the breakdown of where these different stars are. We'll talk specifically about low mass stars, and the sun is included in that group. We're going to start there, and those are basically stars less than 2 solar masses or so. The high solar mass stars that we'll talk about next will be greater than 8 solar masses or so. There is an intermediate range, and the details of what happens there are sort of depending on other factors, sometimes fall into the high mass category and sometimes fall into the low mass category. But for this discussion, it's good enough to break this up into high and low mass stars. Okay, so what happens when the sun, which is going to spend 10 billion years of its life just sitting there burning hydrogen into helium, what happens when it runs out of hydrogen in its core? That's the topic of today's class. And the details of this process are very complicated. It takes big computer codes doing lots of calculations and lots of physics to be able to determine what happens. But there are some cartoon diagrams that we can draw to try to understand what it is specifically that happens and why it happens. So I'm gonna talk briefly about what those things are, and then we'll try to break down the cartoon version and see if we can understand why these things happen. So in the interior, in the core, as you run out of hydrogen, things are going to be contracting and things are going to be getting hotter, and you're going to be burning hydrogen actually at a faster rate. This increase in luminosity being generated at the center pushes the outer parts of the star out. Its luminosity increases, its outer radius actually increases dramatically, and the surface temperature actually goes down. So let's see if we can understand the whys of those things. So here we have a model of a star. You've got the surface of the star, the outer radius out here, and this is the boundary between the core of the star where you're burning hydrogen and the outer, the regular radiative region where you're not burning hydrogen into helium. And so what happens when you run out of hydrogen? Specifically, where do you run out of hydrogen first? You run out of hydrogen in the region of the sun where it is hottest and densest, and that is the place where the nuclear reactions will be happening the fastest, and that is at the very center. So when the sun runs out of hydrogen, it will be at the very center first. You'll have a little patch of helium ash that is no longer generating energy. It's no longer having any fusion going on, and that dramatically changes the structure of the star in that point. It is at some level the energy of that nuclear fusion that was supporting the star. That energy had to get out, and that energy provided a pressure that was holding up layers of the star. When you run out of that energy source, that source of pressure that was holding up those layers ceases to exist. And so what you have is again, a helium ash core at the center of your star that is no longer providing that energy, that is no longer providing that pressure, that is no longer a stable region of the star. So what happens is, again, this is 1 solar mass of matter that is bearing down on the center of this star. And so it will begin to contract. And when it contracts, the layers on top of it will also contract. And so you'll get a bunch of material slowly contracting down on the center. And as material contracts, 2 things happen. The density goes up and the temperature has to go up. And so these regions in the core where you were burning hydrogen to helium before suddenly are hotter than they were before. And the hydrogen fusion rate goes up. They are fusing hydrogen at a faster rate. But that doesn't stop there, right? Because all of those layers on top of it have to contract on top of it. If you're contracting there, you're also contracting here on the outside. And these layers also have to become hotter and denser. And the nuclear reaction rates have to be going up in those regions as well. In fact, there is now a region around the original core where that matter has now been contracted down far enough and is gotten hot enough that nuclear fusion is possible now, even in regions where it wasn't before. So all of this, so you're still burning lots of hydrogen into helium. It's just not happening in the very center of your star anymore. You're burning it in a shell around what is now a helium ash core. And so ironically, against what you might think, when you run out of hydrogen in the very center of your star, you actually increase the star's energy generation rate. You increase the rate at which fusion is going on in other parts of the star, which generates more energy overall for the star. And so the total luminosity that's being generated in the central region goes up. And in fact, it goes up by a lot. And that increase in energy will actually serve to push outward all of the other layers of the star. So the core heats up, contracts and heats up. The nuclear fusion rate goes up. The luminosity being generated goes up. That increase in luminosity, that increase in energy that's being generated provides an increase in pressure, and that pushes the outer part of the star outwards. And so the inner parts of the star are contracting, but the outer parts of the star are expanding and getting bigger and bigger. So what will we see from the Earth? How will this look as if we're still around in 5 billion years or so when this starts happening to the sun? Well, the sun is going to get much, much bigger. How much bigger? Well, it's going to keep getting bigger and bigger and bigger, and eventually it will reach a radius of about a half an AU. That is well outside the radius of Mercury's orbit, and it's almost to Venus's orbit. The planet Mercury is gone. Venus is probably close enough to the surface of the sun that it's also vaporized. The luminosity of the sun, this is not a small effect. We expect the luminosity of the sun in this stage of its life will increase by about a factor of 2,000. The luminosity in this point being 2,000 times the present luminosity of the sun. Now, the radius is going up and the luminosity is going up. The temperature could go up or down if you go back to our luminosity equation. In fact, let's write that one down. Remember, the luminosity is 4 pi times r squared times sigma t to the fourth, where all of these are constants except for luminosity and radius and temperature. So if I make my luminosity go way up and my radius go way up, the temperature isn't, it is affected, but it could be affected in either direction. It depends on how much the radius increases and how much the luminosity increases. In this case, the temperature will actually go down a bit as this process happens. That is the surface temperature. Remember, the core temperature is going up and up and up. But the surface temperature, as these outer layers get pushed out further and further, actually goes down. And that's the only temperature we can really measure directly anyway. So here's a diagram of what this might look like. Here is the sun as a red giant, right? Why red giant? Well, giant because it's gotten a whole lot bigger, right? A diameter of about an astronomical unit. And red because it's gotten cooler. It's gotten much larger and much cooler at the surface. It will move into the red giant phase. We, of course, know that stars like this exist in the universe. Betelgeuse is even bigger now than the sun will get at that point. It is the physical radius of Jupiter extends out past Jupiter's orbit if it were centered on the solar system. Betelgeuse is a much more massive star than the sun, so the sun won't get quite this big, but it is a prime example of a nearby red giant star whose outer radius is enormous and whose surface temperature has cooled off quite a bit. Betelgeuse is in this stage of life right now. Okay, so here's a question for you. Where will it move on the HR diagram? It's getting cooler and it's getting more luminous. Where does it move on the HR diagram? Make your guess. Okay, remember how the HR diagram is fashioned. You've got luminosity on this axis, increasing in this direction, and you've got temperature on this axis, moving in this direction, increasing in that direction. So if a star is getting, let's say it starts here, it's getting more luminous, that means it's moving up on the diagram, and it's getting cooler, that means it's moving to the right on the diagram. So it should be moving generally up and to the right on the HR diagram. And when we look at actual models of how this works, again, the details of exactly how it moves aren't that important, but the sun will leave the main sequence and generally move up and to the right, becoming a red giant, becoming much more luminous and becoming much cooler at the surface. And this is what we call a red giant. And this will be a process that takes, this isn't an instantaneous process. This is a process that slowly moves the star up and to the right of the diagram. As the helium ash becomes bigger, as you use up more and more, and by bigger I mean more massive, as you use up more and more hydrogen, as more and more of the central part of the star becomes devoid of hydrogen, you have a bigger and bigger region, more and more massive region where you have a helium ash core that gets compressed more and more and more. And this process slowly contracts the inner part of the sun, slowly heats it up, slowly makes it increase in luminosity, and slowly pushes, therefore, the outer parts of the star outward. Okay, we'll come back in the next video and talk about what happens next. See you then.